So next we have the president of JX Crystals, Mr. Lou Fraas, with some very interesting new ideas on space solar power.
Yeah.
Do you want the video first or second?
Video first.
Video first.
So it's actually two people, Don Florney, and Don's going to start, and then I'll take over.
Yeah. For those of you who have followed the Space Solar Power Symposium over the years, you see how rich and diverse this particular constellation of papers and discussions really have been. And there are some new areas of interest that now get exposed, and Deliana's presentation represents that, and the one that follows is like that. Louis Fraas is really not a specialist or even a long-term scholar of space solar power, even though his work is very much related to photovoltaics. And he has suddenly emerged with an idea that has attracted the interest of the Chinese, the Japanese, and he's now been giving a similar presentation to the one we'll see today in several venues. It's interesting, so we now have the opportunity to have him talk with us. Sometime during the year, I thought this would be just a very good opportunity to tell a new kind of story about space solar power through digital media. So what we're going to see is a 3-minute piece that has been produced to basically summarize what this is all about, and his presentation will follow.
So before the video, I just want to say that this is a detour from the previous presentations. I'm not talking about microwave or RF. I'm talking about deflecting sunlight with mirrors in space down to terrestrial solar fields. So my background is from the photovoltaic community, both for space and for terrestrial, but it's a different perspective. So I'm interested in economics. I want lower cost, and this approach is a factor of 10 times cheaper than the traditional space power satellite concept, because it just simplifies things, and it uses the existing or to be built PV power plants on Earth. So that it's not 24 hours a day. It's adding sunlight in the early morning and the evening in order to expand the hours for peak power. For example, one of the problems with terrestrial photovoltaics is it's peak power in the afternoon but not in the evening, so this will address that. But it's mainly economics, so it is a change in direction relative to the other presentations. Okay, so you understand that as background.
Okay, just start that.
When you think about solar power, chances are you think of solar panels here on Earth. Yet we've made use of solar panels in space for more than 50 years. The space race was the catalyst needed to drive down the cost of solar technology, enabling terrestrial solar power to develop into a $40 billion industry. Currently, solar installations on the Earth's surface provide a combined 100 gigawatts of electricity, a small number when compared to non-renewable energy sources. But that number is growing by 30 gigawatts per year, and many nations have announced initiatives to increase the amount of solar power entering their grids. These solar initiatives will drive research and development, improving panel efficiency and output, but there are some inherent limitations to the terrestrial solar model. Solar energy reaching the Earth's surface is diluted by our atmosphere, and our planet's unavoidable day-night cycle is the primary problem. This deficiency is most evident in the evening, during hours of peak demand on the electrical grid. If there was a way to extend daylight hours, this would greatly increase the energy produced. And that can be done. Constellations of lightweight satellites with reflective mirrors may sound like science fiction, but the first steps of that vision were completed over 20 years ago. An experiment in 1992 repurposed a routine cargo delivery to Russia's Mir station to test a solar reflector 20 meters in diameter. For several hours, the night sky had a new spot as bright as a full moon. A new space reflector made of modern components will complete the next phase of this experiment. The mirror, a lightweight aluminized membrane, will be stretched flat by 3 radial spokes telescoping from a central body. Control moment gyros, similar to those used in the International Space Station, are mounted inside the central body of the mirror satellite for attitude control and sunbeam pointing. The 3 spokes collapse, folding the mirror membrane into a compact package, allowing several of these mirror satellites to be carried by a SpaceX Falcon 9 rocket. Once these satellites are deployed to a sun-synchronous dawn-to-dusk orbit, they will deflect sunlight to energy-critical locations on Earth. For the first time, solar farms here on Earth will see an increase in sunlight intensity in the morning and in the evening. Both solar photovoltaic and solar thermal sites can benefit from longer daylight hours. As more satellites are added to the grid, additional sites will see improved energy production, increasing the viability of terrestrial solar power and launching a new era of renewable energy.
Okay, so I'm going to get started. I've got 26 slides to go through, so I'm going to try to go through them quickly. So, as the title says, sunbeams from space mirrors feeding solar farms on the ground at dusk and dawn. You guys are all familiar with crazy ideas. So this is the crazy idea, and I'm hoping by the end of my presentation you'll think that it's not quite so crazy after all. So here's what I'm talking about. There's 2 revolutions going on. One is the growth of the terrestrial solar power, which I'm intimately involved in. So as the video said, 100 gigawatts, that's a pretty amazing number actually. And it's actually growing exponentially. It's like it should be 35 gigawatts this year. And that's the blue curve here. So if you extrapolate out 10 years from now, you'll have something like 1,000 gigawatts, which is pretty amazing, but I think real, because I've been following this industry for 20 years, and it keeps growing every year, despite all the negatives you hear from, particularly in the U.S. because of the oil industry. But worldwide, solar is really taking off. The other thing that's happening is the lower cost access to space, and those 2 curves can intersect with a surprising result, which is my presentation. Okay, so it's a surprise that they come together to make solar electricity on Earth more plausible through space mirrors. Here's a quick synopsis. You can see the yellow and black, and then the mirrors deflecting sunlight down to the dawn and dusk areas, and there is related technology. The solar sails made by Lagarde, and I'll talk about that really in the second part of my presentation. But the benefit of this is you can get 14 hours instead of 8. And that, if you take today's cost of solar electricity, which is in sunny locations, not so much in the U.S., but in China, for example, and it's down to something like $2 a watt, and it's close to 10 cents a kilowatt hour. If you take that number and you go and add additional 6 hours to the 8, you get down below 6 cents a kilowatt hour. And also increases the capacity factor that utilities care about. So instead of solar being limited just to the day, it's evening and early morning as well. And the other slides say that there's supporting technology, the space mirrors, and another part will be how to point them, which is the gyros on the International Space Station. I'll get to that. So just to convince you that there are solar fields, and there are large capacity fields, or large. These are 100 megawatt fields or more. 200. I think the one in India is like 250 megawatts, and you see ones in Germany and California, of course. San Diego's big for solar. terrestrial. And it doesn't have to be just photovoltaics. It can be solar thermal with a turbine with hot steam, basically, spinning a turbine. And this is a system in the Middle East, in Abu Dhabi, I believe. Okay, so here's where we started, which you're, I'm sure, very familiar with. When I look at this, I got involved in this because I wrote the first paper on the triple junction high efficiency cells that were proposed for this. So there are now 40% cells for terrestrial. But I know how to make cells, and they're very complex and expensive to make. It is a lot cheaper to coat a plastic substrate with aluminum film than to make an active device. It's much easier to make mirrors than active devices. So I look at this and I say, well, mirrors are good, but there's a lot of problems, and that create cost. One is the multiple conversion steps, because you have to deflect the sunlight to the solar cells. The solar cells themselves cost money. You've got to worry about thermal management. And then you convert it to microwave, and then you microwave down to Earth, and you need a special ground station. So all that seems very complex, but I'm going to keep just the mirror part. And instead of putting it in GEO, I'm going to put it in at 1,000 kilometers up, which is LEO, high low Earth orbit. And so the first part of my presentation will be focused on imagining mirror arrays. There'll still be individual elements in the array, but the total array area would be like 10 kilometers in diameter, and it would consist of multiple mirror segments. In the second part of my presentation, I'll talk about how actually to make the mirror segments, because what I find is that this is economical. So while NASA proposed this and they talked about half-kilometer size mirrors, they never talked about how to make them, because when they analyzed this, it was too expensive to even proceed to the next step. But the system that I'm proposing does look economical, and it is worthwhile to go and just start designing the mirror satellites. Anyway, okay. There is background for the idea of deflecting sunlight from mirrors in space. A guy named Kraft Erika in '78 proposed what you see here. It was part of a NASA study in that time frame. The problem with it was that the concept was still to maintain the 24 hours a day of sunlight, so you had to put it high enough up to avoid the Earth's shadow. And then he put it at 45 degrees and then at 4,200 kilometers up. And the problem is that the sun has a disk size of 1/2 degree, and that causes a divergence of the beam. And that's like 1/100th of whatever the distance is. So 4,200, you end up with a 42-kilometer diameter spot on Earth. And then that's 100 and, if I remember right, 180 gigawatt power station. The problem is, at that time, it was unimaginable. And furthermore, there's a major distribution from that one site. But the concept here was for Europe or for the U.S. Okay, so what I'm saying is I'm just going to put it 1,000 kilometers up in a sun-synchronous orbit, and I'm going to give up on the 24 hours a day, and I'm going to look at the economics of that. And I'm going to assume a constellation. Oh, this is just telling you that it'll cover the Earth from plus or minus 80 degrees latitude, so you can cover the whole Earth with this concept, almost. So here's a lot of detail. On the right-hand side, you see the broad concept, but the mirrors in that concept are very exaggerated in size, but to convey the concept. On the left-hand side, here's the more realistic to-scale drawing. A circle is obviously the Earth, and the distance up is proportional at 1,000 kilometers, and there's 18 satellites in order to cover the whole world. And they really are even a 10-kilometer diameter mirror array is just a pinpoint on the drawing. so relative to the Earth's size. The ground station is similar in size. It's the 10-kilometer diameter size, and that's a 5 gigawatt ground station, which is comparable to the power that the Fukushima nuclear power plant produced. And I drew the circle there to convey the size of this 5 gigawatt station in comparison to the nuclear contamination zone around the Fukushima plant. So it's a problem of scale, essentially, that 10-kilometer diameter seems large, but it's not that large relative to the Earth's size. So here's the benefit. So then the reason why this works is that I'm imagining, like I told you at the beginning, that there is continual growth of photovoltaic power plants around the world. And I hypothesized for the economics, I said, well, I'm going to imagine there's going to be 40 stations distributed around the world. And I tried to check my thought and by starting to list cities, and I got up to 38, and I said, well, yeah, that's a reasonable number. And the only one that's a little odd is Moscow. The others are, you would, well, Alaska is also a little odd. But you have Phoenix, Las Vegas, San Diego, Madrid, Beijing, Cairo, Perth, Sydney. You know, those are sunny locations, is what I'm, Bombay, I'm just scanning. So there are a lot of sunny locations around the world where these, and what will happen, you know, people are not stupid. They're going to put the PV plants in the sunny locations. So then now look at the economics, and I don't have time to go through the whole slide, but I said, okay, there's two numbers that are important. How much, if you assume 10 cents a kilowatt hour and 40 ground stations and 1 hour in the morning, 1 hour in the evening every day for the year, how much revenue would that produce? And the details are here, but it came out 16 billion per year. The next part of the question is, how much will this array or constellation of arrays cost? And that starts out with a weight. And the solar sail provides a weight of 10 grams per square meter from Lagarde in the U.S. And the Japanese have a satellite that's a solar sail on passing Venus now that's similar in weight. So then it comes down to launch cost, and multiple assumptions are possible. Because I wanted to compare it with a space power satellite, I had to use the same number that they used, which is $400 per kilogram. And when I ran that number, it came out the payback time for the mirrors was less than a year, 0.7 years. Now, why is that? That's because the mirrors are always in use, even though any particular ground station is only being used for an hour or 2 hours a day. As the Earth turns, more ground stations come into view. So the mirrors are always in use. That's one positive. Another positive is that the mirrors are very lightweight. And the third positive is I'm putting them in LEO and not in GEO. So that's why the economics really make sense. And I also used a higher number from SpaceX, and that was 1,100 per kilogram sometime in the future, and that came out 2 years. So that was the exciting part of this, is the economics really looked very good. And here it is as a summary. On the right-hand side is the column that's for the space power satellite, and on the left-hand side you see the numbers for this new concept. And it comes out that it's 10 times cheaper. You look at the numbers in dollars per 24-hour gigawatt, 0.7 billion per gigawatt versus 11 billion, I think. So it's 10 times cheaper, and because there's 40 ground stations that are being built anyway, and you're not paying for those. The utilities are paying for them now, so or governments, and you're going to get more energy and more power from the Earth stations than you would get But another point to make is that this is a global concept. It's not a national concept, okay? So if it makes sense to do one constellation, then you can imagine 3 constellations staggered in longitude and get more hours. So if one is economical, 2 more will be economical too. And that's where I said 6 more additional hours. Okay, now I'm going to the second part of my presentation, which is, okay, if this makes economic sense, then how would you start? So what you have to do is build one satellite, one mirror of that constellation. And then if you can build one and launch it and deploy it, and then the thesis is that you could replicate that as many times as you needed. And so I started out with picking a quarter of a kilometer, 0.25 kilometer mirror. Essentially the area of that triangular mirror is equal to what a circle would be at that diameter. And that's half the size of what NASA had assumed in their concept. And at the center of that is where the control moment gyros are that will point this thing. And on top of that center portion is the small solar array, PV, that's needed to provide the energy for the control moment gyros. So the first part of the problem was Worth-Lagarde make a first cut at what the weight and moment of inertia of that concept would be. And then from the International Space Station, you could get the specs on the torques from the control moment gyros. And when I ran those 2 numbers together, it turned out that it does work. So that was nice. So here's more detail, and I don't have time to go through it. The key point here is that we don't need assembly in space. This can be self-assembling, just like the solar sails are now. So the mirrors fold up, the beams collapse, and here's the deployment scheme. So it's so that's another plus. You don't have assembly in space. It self-deploys. So this is the summary of just that part of it, the design of this mirror satellite, using existing programs like solar sail programs and like the International Space Station. Okay, so then I'm going to work towards the last view graph, which is a roadmap. And so the problem is, how do you get there? I mean, and that's the problem we've all had with the space power satellite concept. So one concept that's been around is that you could use mirrors in space to deflect sunlight down for municipal street lighting in the evening. And so I ran that. That only requires 20 of these satellites, which would be something like 5 launches from Delta, today's rockets. And I used $3,400 per kilogram, which I noticed was in Gordon Woodcock's presentation in the morning, was their starting assumption for beginning a project of this type. The $400 per kilogram is more like, in Gordon's talk, he had 370 or something like that. John Menkins has made a presentation, or I've seen his NIAC report, and he points out that as volume of launches goes up, costs come down, which is obvious. But those numbers that I'm using are not unreasonable compared to what other people have used. That came out to be $70 million, not billion, and it's a 4.5-year payback time. This is the last slide. So here's the roadmap, 4 steps. Step 1 is the experimental step, build one with maybe NASA support and maybe some private company support, and use it not only to prove the technology, but also for entertainment at night 4 Disney parks around the world is one concept. And then the second step would be the 18 mirror satellites for street lighting. And then the third step is the first constellation, and then the fourth step is the next 2 constellations. And at the end, you end up with 37 billion, which is 10 times less than what Gordon Woodcock was talking about. But it's also, while it's a big number, it happens to be very comparable to the Three Gorges Dam project that China did. And that cost 37 billion and produced 22 gigawatts. This would produce 54 gigawatts, about 2.5 times more energy on a 24-hour basis. And it's more efficient land use as well. So that's the end.
Well done.
So questions, I'm sure there'll be many. And by the way, before we get into the questions, we were talking about possibly being able to get together at some point with the other people that are interested, just to, because this is a new idea. So I don't know how we're going to organize this, but this may take longer than whatever time we have left, 5 minutes.
You'll be at the conference until when?
I'm here until Monday mornings. Well, I'm leaving on a plane at 5 o'clock on Monday morning. So I'm here Saturday and Sunday all day.
Good.
So what is the power density at the surface of the Earth if you're working with PV field?
It's one sun, is what I assumed. We put enough mirrors up there, and that's where the diameter came from, in order to get one sun intensity on Earth.
Okay, just one more follow-up question. So what's the approach angle? Because PV is typically oriented, fixed cases.
You have choices there, but if it's just horizontal, then it still works. But a lot of the utility-size PV systems are using one-axis trackers. They track from east to west. So these mirrors at dawn and dusk would be essentially overhead, so which is not inconsistent with just laying the PV panels flat. But if you're talking thermal, where they actually are using troughs and east-west trackers, that would work too. You'd just reorient the tracker to pick up the mirrors at dawn and dusk, and then go back to picking up the sun during the normal day, and then come back in the evening to the mirrors. So one-axis tracking works just fine with this, either with silicon PV or with the trough thermal systems.
What's the average capacity factor that you're able to?
Well, it comes up to be, I think it was on one of the view graphs, it's close to 60% instead of 33, I guess. And by the way, I'm talking about sunny locations. I'm not talking about Seattle. So these are select sites. Let's see, who else?
I got one solution followed by 2 small problems. The solution is you want to spin this at the altitude you're at. You want to spin this about 3 divided by root 2 turns per orbit.
Yeah.
Why is that? Because you've got these things tilted. They're under a fairly heavy gravitational torque, which is basically 3 omega squared, 3 over r squared. And so if you turn them that way, the additional torque from the gravity torque will turn your mirror the way you want. There's no natural way to turn the mirror the way you want.
I have two versions of this presentation. The first version was this idea. I first talked about this in last July, and in that case, I was using gravity-stabilized mirror array with on the International Space Station. They have a way of pointing the arrays. So I've forgotten what they call them, but the motors, essentially, the motors that are pointing the PV arrays on the International Space Station could be used to point individual mirrors in a gravity-stabilized frame. The problem with that was that you needed assembly in space, so then I came up with this second concept where you don't need assembly in space. So I'm not sure that this is a final. I'm sure that it isn't a final thing.
Take your determined out with a whole lot less work, just with the physics The other is by flattening it, you can keep the diffuse reflection down. That's going to be a big problem, but we've talked about that a little.
Quick note, lunch is in 5 minutes, so if you need to excuse yourself for lunch, this would be a time to do that. We're officially into our break period, but this can continue on if you guys have further questions.
No, why don't you help answer identify the people? Go ahead.
Are you concerned at all about the slewing away from the site where you're transiting through populated areas?
Yeah, I've thought about that, and the first comment I can make about that is that this is an array, and what you're doing is coordinating all the mirrors in the array to point at the PV site to get one sun. But when you slew to the next site, you don't have to slew them all simultaneously. You can slew them in succession, so that in other words, anybody on the ground might see a moonbeam for, I don't know how many seconds, and a fraction of a second instead of a flash of sunlight. So you could stagger the mirrors by a few milliseconds from each other to.
It'll be longer than that because it's not going to be, moonlight's 1/400,000th as bright. It's going to be much dimmer than a full sun, but it's going to be a lot brighter than sunlight if you're actually going to slew them quick enough to be useful.
Well, the slew.
Slewing individual ones.
The slewing that you're doing is over like 6 minutes. So if you spread it out over a minute, it'd still be all right. I mean, even a half a minute, you'd probably do all right. And then yeah, there's going to be a lot of coordination required to make this all work in terms of semiconductor chips that are things that we know how to do with computers. There's going to be a lot of coordination, and what I'm trying to say is also a couple other points is. People talk about cloud cover. Well, you don't, if you're smart, I mean, if these systems are smart, then you could choose which of the PV fields you want to illuminate depending on cloud cover. So you have that option. And also you have an option of where you're slewing from to. I mean, you don't have to slew over major city population areas.
This is a dynamic system. You can take advantage of that. You have dynamic control. You have to have dynamic control to support it all, so you can take advantage of that.
Take one more question, and then we'll break up and have informal talks. Keith?
What have you done on, and how much does it cost mostly to deal with the reaction forces from light pressure?
Oh, I've looked at that. And actually, compared to gravity, the light pressure is very small. So to be specific in answering your question, if you have 1 pound of force on the ends of the beams, you can keep the mirror flat to within, I think I did the calculation for 2 milliradians.
I'm not talking about keeping the mirror flat. What I'm talking about is the thing being blown out of orbit.
Okay, I've looked at that too. You'd have to divide those force vectors into 2 components. There's the one that's the radial component, and just remember that the position of the satellite in the orbit is controlled by a balance between gravity and centrifugal force. So what you're doing, you slow the orbit down by a couple seconds to account for that radiation pressure you're talking about, and then that's a stable orbit. Okay, you see what I'm saying? I mean, you're balancing forces anyway.
I'm familiar with the concept because, for example,
We're going to take a dialogue, and let's do this informally, but let's give them a round of applause for it. That's great stuff. Thank you very much.
Okay, I enjoyed meeting you finally, and you've done a great job in organizing this meeting, so I appreciate that.